Neil Thompson, research scientist at MIT CSAIL, which is the Computer Science and AI Lab. Welcome to the Data Exchange podcast.
Thank you. Pleasure to be here.
And Neil, you've had a varied career, as we were talking about right before we started recording this. But I have you here specifically because you and several collaborators just wrote this fantastic paper titled "The Computational Limits of Deep Learning." So I guess the first question is, what was the genesis of this paper? How did you guys end up working on this paper?
Yeah, so this paper came out of being at MIT, and we're very lucky at MIT to have a parade of really, really interesting people doing cutting edge work coming through. And I was struck that every once in a while, someone would sort of give a hint about the scale of computation that was involved in what they were doing. And the numbers were sort of eye-watering. They're like, oh yes, we did this and then we ran it for 3 weeks, or we had this whole set of GPUs that we were running on, and you just kept hearing this again and again. And I thought, okay, this pattern that is emerging is one of an enormous amount of resources being devoted to these things. And as someone, part of my training is in economics, and I thought, okay, this is something I want to hear more about, because I think we almost always hear about all of the amazing things that are going on in terms of the achievement, the performance. And I wanted to say, yeah, but what are the resources we're putting in, and how are those two things relating? And of course, the worry being, could we get to a point where we're putting in so many resources, or we have to put in so many resources to improve performance, that things might slow down for us in terms of getting more progress in this area? And so that's really sort of what led to it. And then just starting to say, okay, well, let's try and do data collection to see if we can get a larger scale rather than just an anecdotal view of how that's evolving.
So actually, there have been groups actually from your alma mater, UC Berkeley. There were some people out of AmpLab back when it was in operation, now called Rice Lab, that did kind of calculations in terms of not economic per se, but more like how many floating point calculations do we need to make to do certain things. And even back then, the numbers were enormous. But then, why do you think? So I guess the answer probably is twofold. One, there's enough improvements in pattern recognition type applications that people forged ahead. And secondly, I guess it was still within the realm of affordable, right? So, but why do you think people keep forging ahead in this direction of let's throw more and more compute?
Yeah, so I think the short answer is that as long as we are sort of breaking new ground on what we can do, there's a strong desire to be able to do this, right? And so I think, if you are someone who's interested in machine translation or image recognition or any of these areas, speech understanding, right? We know that these are very exciting frontiers of computer science. And so, even if you say, well, yes, I had to use an enormous amount of resources, but I got 2% better than the last model that had done this, and that allows me to maybe roll out something. If you think about voice recognition on our cell phones, right, that's been transformative of how we interact with them, even though it's still not perfect and we're still working on it. And so I think that's what has pushed people in it, and I think it's the success of these methods that has led them to do it. I also think that there has been, and maybe still is, this view that maybe we will save ourselves by coming up with better algorithms. Right. And so, when people have done calculations in the past of sort of like the theoretical, how do I scale this particular model or that particular model, right? That sort of abstracts away from, well, maybe the next time I implement something, I've figured out some new key aspect to it and I can make everything 10 times as efficient or something like that. And so that's why for us, it was so important not to look at it just from a sort of a theoretical view, but actually do an empirical view and to go to all of these examples over the last 8 or 9 years and say, in practice, when we take into account both the performance people have gotten and all the algorithmic improvements they've done along the way, how have these things evolved? And we see even with that, there's been this enormous scaling, right? And so I think that that's important to say. You might hold out this hope that we're going to sort of come up with a magic solution, and there's still room for algorithmic improvement, so we still might make a lot of progress there. But I think some people have this hope that sort of that's going to take care of it, and I think what we see is so far, actually, we've continued to need to throw many fold increases in computing power in order to keep moving progress forward.
And to our listeners, I will definitely link to the paper in the show notes, but I just discovered in preparing for this podcast that there's actually even a short version of the paper, which is also great for people who want to save some time. But Neil, so at a high level, let's give our listeners a flavor of what you found, because some of the cost calculations that you guys that your team did, that as you lower the error rate on some of these benchmarks are just insane, right?
Absolutely. So maybe here it would be helpful to give a little bit of context for sort of how these networks have developed and how we sort of got to where we are today. So if you go back to 1960, Frank Rosenblatt at Cornell has this idea of, I'm going to create a network that is going to look like the brain, right? Or in particular, inspired by certain nerves in the brain and the way they work. And he comes up with this idea of a perceptron, and later we call this class of things neural networks. And even in that very first one, which is going to be the precursor to deep learning, even in that very first paper he writes, actually, as I apply this, I think it could be a good pattern recognition technique, but I'm worried that we're going to run into the computational limits of what our computers can do. So that's the very first paper, right? And in fact, this problem basically gets worse in the 10 years that follows it, because people realize, including Seymour Papert and Marvin Minsky at MIT, that some of the key things that you might want to do with a neural network actually cannot be done when it just has a single hidden layer. And so they say, oh, we can get around this by making these networks deeper, but of course that comes with a huge increase in computational costs. And so we really see for quite a long time after that, the size of the networks that people are building basically just grow with Moore's law. Right, and that's a really important thing to keep in the background here, because from about 1970 until today, we have something like a 50,000x improvement in what our chips can do, coming from Moore's law. And so that gives us more and more computing power. But for most of this time, as that's coming along, neural networks are using this extra computing power, but is only in the late 2000, the early 2010s and the late 20 knots, I guess, that we see a real shift to saying, actually, we can come back, we can build these neural networks big enough that they can handle these problems. So I think that gives us sort of the context of how we come in here. And so what we did is we said, okay, well, now let's look at how these models scale. And what we find is that there's this large penalty that you pay in order to improve performance. So tell me if it would be helpful here, I could take a second and talk about why, at least from a theory point of view, you think you might need more data to learn from things, and then come back, or should we jump? I can jump also right to.
I think sure, yeah. I think people have heard at a high level that these deep learning architectures start excelling when you have more data.
Yeah, that's right. That's right. And so I think there's sort of two things to think about here, right? So if you think about how the performance of deep learning scales, the first thing is something that is much more general. So it actually comes from statistical learning theory, but it's this idea that as you learn from data, the first pieces of data you have give you a lot of information, and as you gain more and more, you get less and less information that comes along, right? And so I think of this sort of as a nice analogy of when people go out on the dating market and they're trying to find that special someone, right? The first date is very telling. Second date also helps you a lot. The 50th date, you're not learning that much new information, right? And so it turns out statistical learning theory tells us that if you wanted to improve performance by some factor, then you have to add an amount of data points at least equal to the square of that. So if you want to improve your error by a factor of 2, you got to have 4 times more data. Factor of 10, you need 100 times more data. So that's the sort of like statistical part of this whole thing. But then there's the actual engineering of us building these deep learning systems. And an overarching theme that we do with these models is over parameterization. So we want to have more parameters in the model than we have actual data points that we run on. And you can sort of think of that as just like more computational machinery that we're going to carry along with us when we process each data point. But what that means is each data point that you process becomes more expensive computationally. And so if you add both of these effects, actually you get a thing where if you want to increase performance by some factor, you have to increase the amount of computation you use by at least a factor of 4. And so now all of a sudden that 10x improvement in error, right, becomes a 10,000 increase in computing. And that's, I think, why things are so expensive at a fundamental level. Of course, what we show is that actually that performance is even worse. So if you go to something like ImageNet, you would say, okay, well, we think the theoretical best you could do is scaling to the power of 4. Actually, it looks like people are scaling more like to the power of 9.
So let me clarify here. So everything you've said so far is theoretical, but also observed empirically over time as people beat these benchmarks.
That's right. Exactly.
And then secondly, I think it's fair to say that even though the models are somewhat over parameterized, the community has some tricks around regularization to make sure it's not overfitting, right?
That's right. That's right. So that's a very important thing, right? I always am reminded when I first heard about overparameterization as a technique, I sort of flashed back to my high school algebra classes, right? And this idea of like, well, we're going to have more unknown or more equations than we have unknowns, and you're just like, well, I'm not sure how that's going to work, right? And so it is a very weird thing, and it's but just as you say, it turns out that this idea of sort of starting to train these networks with lots and lots of parameters, but then stopping after not too long, turns out to provide this regularization. And so we don't end up overfitting the data and fitting noise rather than what we want, which is like the deeper statistical pattern of what's going on in the data.
So then the other thing that I think I liked about the paper is that there's a variety of things that you folks studied. It's not just computer vision, it's speech, it's text, right? So it's across all these different data types and domains.
Yeah, that's right. That's right. And what we were really trying to do was establish, like, is this a pattern that we can see more broadly that is probably something about the way the machinery of deep learning works rather than some vagaries of one particular domain versus another domain.
Okay, so now let's go back to the insane economic numbers that is just mind-blowing, some of the numbers that you folks came up with, even in computer vision, right?
Exactly. Okay, so let me give you some sense of this. So back in 2012, there's this paper, AlexNet, which comes out, which is very revolutionary, right? It's sort of the first one that proves that deep learning can be state-of-the-art in image recognition. And in the years that follow, everybody says, okay, we have to use deep learning for this problem. So from that,
the first group that actually learned how to use GPUs for this, right?
Yeah, well, so there was a little bit of work. There had been some work that had been done at Stanford by Andrew Ng's group about being able to first port it over to GPUs. But I think it was this group at Toronto that really showed bringing that to ImageNet, one of these competitions, and showing how much gain they could have. It is also important, by the time that they did it, the actual gains were even larger. So the first group finds, I think, is at something like a 10x improvement, and by the time it gets to the group at Toronto, they're getting something like a 40x improvement coming from the specialized chips. Yeah. Okay, so from AlexNet to the biggest models that we see in image recognition today, you have something like a 10,000 times increase in the amount of computing that's being used.
Wow.
An enormous escalation, right?
And we're talking 8 years?
Yes. Yeah. Mm-hmm. Okay. So, and it's important to say that, some of that is coming from people are making better and better GPUs, and so you can run stuff faster. But a lot of it just comes from using a whole bunch more GPUs, running them for longer, and so all of that comes with sort of additional environmental costs and stuff, which I'm sure we'll come back to. So you say, okay, we see this increase, and what you can do is you can fit that line and say, well, what would you need to do in order to get to, say, a 5% error rate with ImageNet, okay? And as you say, the numbers are pretty eye-watering here. So you would need 10 billion floating point operations, okay? So, 10 to the 19 gigaflops. So that's an awfully large number. And that immediately tells you that is about a factor of 10,000 above where we are today, right, in terms of this. And so you can again start to think about that in context of, I told you before that Moore's law from like 1970 till 2018 gave us something like 50,000 times improvement, right? So it is an enormous amount of computing progress that we would need to get in order to be able to really harness this.
So actually, is it fair to say, Neil, that of all the areas you looked at, which one would be the most demanding? Is it text? Because now you're hearing about these transformer models that have billions and billions of parameters, right? And by the way, it's not just computing that is failing to keep pace in some ways, but even memory needs to keep pace, right? Because you've got these models that have enormous number of parameters, so you need more and more memory. So first of all, it's impossible to not scale out and do distributed computing at some point, right?
Yeah, so I mean, I think so to your first part of your question, yes. I mean, I think we definitely see some of the worst scaling in our results coming from things like machine translation. Now we need to be a little bit careful because in some of these areas, there's just a lot less data. These are sort of newer areas of applying deep learning, and so given that we're trying to draw this historical trend, we don't want to take too much into the exact specific number there because we don't have as much history. That's one of the reasons that we have in the paper we focus more on image recognition is precisely because we have more years of data in order to make that prediction. But we do indeed see this big escalation. To your other point, I think you're absolutely right. I mean, when you have this amount of escalation in the amount of computing, and as you say, the amount of memory that you might need, if our computers don't improve the way they were in Moore's law, right? In Moore's law, they were improving exponentially, and so actually we were getting those things. In an era where that pace has slowed down dramatically, you have to then just multiply the number of machines you're using or use them for longer and longer, and of course that just comes with much, much higher costs.
And before we go to the last section of your paper, which I also love, which is on the potential alternatives to what we're doing today. So what has been the reaction to your paper from the deep learning community? Has it been denial?
No, I think the biggest reaction we've had is sort of an appreciation, because I think a lot of people were aware that this was going on, but sort of we didn't have like one data set that put a lot of these pieces together and really showed like how bad it could get. I think the other thing that I've heard is an appreciation from people who have been trying to use more efficient machine learning techniques or other machine learning techniques, because deep learning has been so hot for 8 years now, right, that they're feeling a little starved on the grant side and on the attention side. And one of the things that our paper implies is that if we cannot improve the efficiency of the way we're doing deep learning, we're going to run into these sort of crazy numbers that we just talked about, and that's going to force people to either slow down or or move to other techniques. And so I think for those people, they're saying, well, I've already tested in this area and I can already see that computation is going to be restriction, so I'm moving to this other technique. And I think that's a pretty helpful thing for them to be able to say, because I think there'll be a lot of value to the community if we can come up with these better techniques.
Yeah, and I also like thinking of machine learning in some ways as, if you think of machine learning as search, you're searching for a function, right? But if everyone is searching in the same area in the function space over here, everyone is searching in deep learning, there's maybe there's a lot of ideas over here that in another domain, another approach that people are not, all the intellectual firepower, all the compute is being used in one area, which also I think, Neil, has implications for how like you said, funding and research, but also how people perceive of, okay, so if I want to be competitive in this world of machine learning, I should probably not go into academia. I should probably go into one of these big tech companies or something, right? So it has implications for how people make career choices too, I would imagine, right?
Yeah, so that's actually a really good point. So there's some interesting work being done right now by some students that I've met with who are talking about this precisely from the aspect you're saying, because one of the implications is that if you need what is effectively a supercomputer in order to run your models, all of a sudden the number of places that you can go to actually do this kind of research dwindles very quickly. Now, I wouldn't want to discourage people from coming to places like MIT because, in fact, fortunately, I think we're in a privileged place where we often negotiate with these big companies to get access to their machines as well. But it is absolutely the case that what this student is seeing is that there may be some concentration happening as people focus around who has access to these big machines. And so, just to your point, I think that does speak to these big resource requirements. Place a burden on researchers, which you might worry about as well.
So by the way, so we've been talking about deep learning, but the other hot technique that I also actually like a lot is reinforcement learning, and that requires even more compute, right? Because in many ways, in many of the headline grabbing applications, they're actually starting from first principles. They're learning everything from scratch. So they're just letting these things rip for months probably.
Yeah. So one of the things that has been interesting to me as I've gotten as this paper has come out is that you start to hear stories about some of the places where people have run into these barriers. So you mentioned GPT-3 before, and OpenAI, which is the group that built it, has had an enormous amount of success with it. But it is interesting because you can read when they discuss it how they realized at one point that there was an implementation error and they'd sort of mixed a little bit of the data together, and then they said, but we didn't retrain it because it would have cost too much to retrain it. Right. And, it's estimated that it probably cost them more than $4 million to run it. So that's not a surprise that they did that. But those are the kind of things that you hear more and more, like similarly, DeepMind. So when they did the StarCraft game, there were a bunch of places in the model where they needed a system to do some particular thing. And they didn't test a whole bunch of different ways of doing that. They picked one and just stuck with it because they thought, well, it'll probably be good enough, and we can't afford to retrain this model each time to try all of these different things. And so I think, again, another consequence of this is that this cycle that computer scientists often like to be in, where they can sort of test or build, test, and then revise, right? Actually, that having a quick cycle there depends on not requiring too many resources in order to run your model. And so that's also a little bit at risk when we have these models that require so much.
And then there's I think the other thing that we should probably emphasize is people also hear a lot about these new hardware startups, right? So these specialized accelerators that excel at matrix computations. But I don't think we can say that hardware will solve all the problems that you're talking about, right?
Yeah, no, I don't think so. So, so let me if talk about hardware, let me just split it apart into two sort of pieces. I think there's like a near-term piece and a far-term piece, and I think it's important to take them separately. So the near-term piece is, I think very much what you're talking about is people started out by running these systems on CPUs, and then they said, oh, well, we'll move them to GPUs. And then people like Google said, well, we're going to design our own ASIC to do just the computation we want for deep learning. That'll be a chip that'll be specifically for that for us. And lots of people are coming along and saying, well, I have this other way of building this chip that will do more. And it's clear that we've gotten probably at least a factor of, between say 40 and 300 from these kind of improvements. So that's pretty substantial, no question about it. But the problem with hardware specialization, and actually some co-authors and I wrote a paper in Science not too long ago talking about this, with hardware specialization is that it's a decreasing marginal returns thing, that as you specialize more and more and more, when you first start to specialize, you take the thing that gives you the biggest advantage, and then you do the next one, and the next one, and the next one. And so incrementally, they become less and less impactful on your overall outcome. And so I'm very, very skeptical that these improvements will lead us to the kind of massive increases that we would need. So I think that's the near-term picture. I think in the longer-term picture, there's a question about things like quantum computing or some of these other hardware substrates that you might be able to plug in there. And of course, everyone sort of says, well, quantum will solve everything, right? That's a little out there. I do think, the thing about quantum computing is if you could get it to work in this area and get an exponential increase in speed, which I'll talk about in a second, if you could get both of those things together, then it is clear, because adding qubits improves your computing power exponentially, actually that would really solve this problem for sure. But as near as I can tell, we neither have successfully implemented it, nor have we come up with a algorithm in quantum computing that will give us a big speed up over what we can do on a conventional computer. And so I think we are a very long way from any of those coming to be manifest in the next at least decade.
So you had already mentioned this, that part of the machine learning community, at least the ones that are not working on deep learning, have reacted positively to your paper. And I have to say that I've been one of those people that have been kind of saying that probably since 2016 that we should probably look at other things, because you can't have everyone looking at the same thing. Number one, and number two, I just think that and maybe I've been proven wrong, actually, Neil, because I always around 2016 I was thinking, well, if you look at the pattern of new RIPs, right? So every 5 years or so, there's a new wave of techniques, right? So you had support vector machines for a while, Bayesian people. But now we've had deep learning for 8 years, and there's no signs of it getting dislodged, right? So I on the one hand, I'm with you. I would love to see people come up with more efficient techniques that can compete, at least on the pattern recognition side, with deep learning. But a couple of things. One, the big tech companies have made investments in this, and so they have a lot of people, a lot of data, and just a lot of incentive to keep going down this road. So if let's say in the pattern recognition side, right, so in computer vision, do you think it's plausible that someone will come up with something that's not deep learning based that would be competitive?
I do. Yeah. So I think that so when I think about this question about like how successful deep learning has been, I think a lot of it comes down to sort of fundamental flexibility, right? So there are these very nice, this very nice set of research that has looked at neural networks and has said, if you have a big enough neural network, you basically have a universal function approximator.
But that's like, true for kernel methods too, right?
Oh, exactly. Yeah. Exactly.
Yeah,
right.
yeah.
Right. And so what I would do is I would say, deep learning is one of these systems that is enormously flexible, right? And as you say, in fact, some of these kernel methods are as well. But it happens to be a very flexible method that is also very, very parallelizable, right? And so, before when we were talking, I was mentioning that Moore's law was really important. One of the key things that happens when Moore's law starts to slow down in the mid-2000s is that it's things that can be parallelized that continue to get some benefits, whereas things that can't be parallelized more or less plateau quite quickly. And so the fact that deep learning can be parallelized and is moderately efficient in the way it handles things, actually those things really lend itself to saying we have an enormously flexible method that has continued to have a big gain in terms of the hardware that you can build for it and the sort of last gasps of Moore's law that you can use for it. And so that's why I think that it's been so successful, because it's very flexible and uses computing power that we have now very well. I think, though, so I think the place that's going to, I think what will happen is that people will say, well, I'm going to use this other technique, not because I think that I can't fit it with deep learning. I could fit it with deep learning if I had enough computing power, but I'm not going to have enough computing power to do that. And so I'm going to have to go to another technique.
So they have to be clever. They have to be clever by default almost.
Exactly, right. And so I saw some work being done here at MIT quite recently, which was very nice, where people were trying to do image recognition, but on cars. And one of the interesting things about cars was that you actually can get these engineering plans for them. And so you don't have to sort of say, well, I'm going to learn them from scratch. You can start from saying, I know how this should look. And actually using techniques that are actually much closer to regression, they're able to do very, very well and outperform deep learning networks on those. And so I think that's an example where if we can start to bring some expertise back into our models, that'll allow us to make them more efficient. And I think that's what will allow people to start beating deep neural networks at some of these problems. And of course, I think one of the things that will also happen is people will start mixing these networks. They'll use the deep learning for the part that needs to be flexible that they don't understand. And they'll have like expert modules in the places where they do understand it. And those expert modules will be much more efficient. And so that will make the overall system more efficient.
Yeah, so let's use domain knowledge and when we have it, right? So actually there's I saw a funny post from my friend Ben Recht. I don't know if you know him. He's a professor here at Berkeley, but so he showed, I think it was one of these robotic tasks where the robot would catch a ball in a cup. So the first video he showed us, so here's a video from DeepMind. The cup was enormous, right? And then the robot caught the ball, but apparently this took massive amounts of compute. And then right after, in the same conference, another speaker right after gave a talk. The speaker came from Optimal Control, so he just trained his thing in a laptop, right? So boom, the cup was much smaller, much harder catching configurations, no problem. You know.
Right.
Yeah.
Right. And it is kind of remarkable, right? If you read the history of some of these things like machine translation, you go from an era where we use a lot of domain expert knowledge to the thing where we sort of have, taken it away and just said, well, we're going to build these flexible systems. And so just like that, I think we'll incorporate some of that expert knowledge back in to be more efficient. And it sounds like that was a great example of how big an effect that could have.
And honestly, if you look into Neil in each of these fields, computer vision, and more recently NLP, you talk to the old timers in computer vision, you go, oh man, the computer vision is basically deep learning. The students really don't need to know anything about image processing anymore, because before we had to handcraft all these features. You had to know a little bit of some of these techniques. Now everything is deep learning. So now NLP, I don't think is quite there, but I think it's beginning to be kind of like that, right? So where maybe you don't need to know as much about computational linguistics or something like that, unless there's so in other words, if you go to one of these computer vision conferences 10 years ago, it would be unrecognizable today, I think.
Yeah. Oh, absolutely.
Yeah. And so what besides kind of this speculation around people coming up with clever techniques, what other possibilities do you see on the horizon? I mean, because at least unless someone comes up. By the way, Neil, so when it comes to these clever techniques, to move the needle and to attract the attention of the large tech companies, what would have to happen? Do you actually have to beat them at the benchmarks, or do you have to come? You just have to come close, right? And then you're more efficient. Maybe that's enough for them to pay attention, right?
Yeah, so I definitely think that you can get attention in either of those dimensions, right? Now, I think the flashier one, the one that gets you more, is to be able to beat them on performance, right? And so clearly, if you can be more efficient and translate that into being able to do
Man,
more, I think that's probably the thing that gets their attention
that would
most.
be like a super game changer, right?
Exactly, exactly. But I also think that
So I'll put you on the spot. Put a probability. What's the probability of that happening in the next 5 years?
oh well, that's a super hard question. I don't think I have a good answer except to say that
It's not zero.
the no, and I mean I think the fact that we continue to see architectural modifications to the deep learning systems that are being used in these areas suggests that there is a lot of work that is being done to think about like either how do you use computing power better or how do you do things more efficiently. So it's not that people aren't thinking about these areas, right? It's not that someone has just taken sort of the AlexNet and just simply scaled that model. People have come up with different architectures, so they are thinking about these things. I just think that it's the area where you get the most publicity, the most recognition in the community is if you can beat the state of the art in some area. And so, but I think that nevertheless, if you're thinking about it from a commercial side, because implementing these models at scale often itself requires a lot. Like most of the stuff that we've been talking about today is all about training these networks in the first place. But if you then deploy them, right there, the efficiency matters a ton, particularly if something like that's on everybody's phone.
Right.
And so those are the kind of applications where I bet you that efficiency would be both heard and really appreciated at the commercial side.
Right. But even if you have a very good model on the phone, chances are you trained a massive model and compressed it.
Yeah. Yes. And so precisely one of the things that that we thought about was these initial training costs, because there are a number of techniques that people have used to try to come up with models that are cheaper to implement. So as you say, maybe you train a big model and then you prune away a whole bunch of the connections that don't matter, or maybe you do sort of a neural architecture search. So you grow a whole bunch of different models and try and pick the ones that seem best. And so you're doing those things. Those tend to increase the cost of training in order to improve implementation. And that's, if you're doing a lot more implementing than you are training, that's a good deal. But it doesn't solve the problems that we're talking about in this paper, because these are really the training costs that we are talking about the most. And so those problems persist with any of those.
So have you been following Mike Jordan's? Mike Jordan has been giving these talks about machine learning in markets, economics, and things like this. Basically, I think the gist of it is that a lot of what we have talked about in this conversation actually has to do with pattern recognition. So there, maybe deep learning has really excelled, but there's another class of things around decision making where it's not clear that deep learning is going to dominate. And so maybe there, especially Neil, when you start getting into causal reasoning and things like this, right? So, so maybe there, people from other schools of machine learning, working with people in other disciplines like economics and game theory, can make progress.
Absolutely. So this is something that I really experienced. So I actually did my graduate work at Berkeley. And as I said, I have some economics training, but I also did a master's in statistics there in causal inference. And you could really see the tension that exists within statistics about some people are saying, well, it's all about the prediction. And some people are saying, no, I really want this causality part of it. And I think it's really going to speak to sort of how often we think the sort of underlying training data basically ceases to be true, right? And so if you're in a world where, like, yes, we have agents making decisions, but they're within sort of a relatively constrained range, I think actually prediction probably will still do fine, right? So if you think about the game of Go, right, AlphaGo didn't know the decision process, but it's still new enough to be able to make good predictions.
Right.
I think the more worrisome thing is if you think like, oh, we're going to try and predict something about, you know, how humans react to technology or something like that, and then you say, well, but then the technology changes, and we might really lose that ability to do the predictions well.
So what's happened to the whole Judea Pearl school? Are you familiar with that?
I am,
Yeah.
yeah. So I certainly can't speak for the whole thing. I just can say that in
Is it
the
as
community that
far as
I've seen.
when I say happened, practical applications?
Yeah, so I mean, unfortunately, I don't think I know the answer to that very well. What I has been struck though is that I am seeing more and more instances where people are trying to incorporate that into other types of graphical models or other types of learning. And so not necessarily on the commercial side, but more on the research side is what I've seen. But it certainly seems to be that you know, some of the machinery that comes with that is very useful for testing things and sort of searching through data in an automatic way, but in a way that still gives you causal properties. And so that seems quite interesting to me, even though as I say, I don't know of any instances where it's already in application, although you know, lots of those could be in, and I just wouldn't know about them.
So what's next for you and your collaborator in this line of research and thinking?
So a lot of where we're going corresponds to very much where your questions took us, which is the current research says we are running into these speed limits, right? We are going to say, you know, we've been accelerating, and all of a sudden we're going to hit things where you say, like, are you really going to spend tens or hundreds of millions of dollars to train these models? You know, I think most people will say no, and so the question will be, well, what do you do then? And so part of what we want to do is say, well, if you move to expert models, like how much of a benefit could you expect that comes from that? Part of it is
we're not talking about handcrafted rules, are we?
No, I think not, but I think it's trying to take advantage of structure.
Yeah.
So there's some very, very nice work, for example, that was done at MIT by Silvio Udresco and Max Tegmark, for example, that showed that you can use a deep learning neural network, and then you can actually basically distill it down and make it simpler and simpler, not just in sort of a pruning way, but in a more like totally re-architect the network way. And that actually can make it much, much more efficient. So I think that would be the kind of thing that I have in mind when I'm talking about that.
Speaking of MIT, actually, I like what Josh Tenenbaum has been doing, right?
Mm-hmm.
Yeah.
Yeah, so I've been following Josh's work for many years, right? This is, you know, for your listeners who aren't very familiar, a lot of it is about bringing in some of these sort of statistical concepts about sort of from learning theory and sort of some of the things that we think are going on with the sort of Bayesian learning techniques that humans may be doing, and bringing those in, doing some probabilistic programming or symbolic manipulation underneath the hood. And, you know, some of the neatest things is, of course, some of this few-shot learning, where instead of having 10,000 examples of something, you might be able to learn something with 2 or 3, for example.
And in closing, very briefly, Neil, for our listeners out there, they might say, well, I'm just in a regular company. We only have structured data. What does this have to do with me? What say you?
So I think what it says is that you know, if you're sitting back and watching this, you know, cascade of changes that is going on in deep learning, right? It says, first of all, don't throw, if you're doing other stuff, don't necessarily throw it all away, right? You know, you have to think about the trade-off that's going to happen in terms of the performance you can get in the computation and stuff that it's going to cost you. So I think that's the first thing. I think a second thing people need to be thinking about, though, is these dynamics that you were mentioning about how if all of a sudden you need more and more compute for these models, that has the potential to have some economic consequences, like pushing people towards an oligopoly or a monopoly in some areas, because only one person might have enough data and enough compute to actually do the model that is really important. And so in industries that are really focused around just a very small number of important predictions, actually you could imagine this playing out in economic ways, which would matter a lot. And so I think those are the kind of things that if you're on the commercial side, you need to be thinking about how this plays out. in your particular industry and given the models that you care about in order to make the predictions that matter for your
And
business.
actually, as you were talking there, I just realized, and there's also, on the public policy side, there's the arms race between countries, specifically U.S. and China.
Mm-hmm. Yeah, so I've actually been doing some work on this recently. We don't yet, that's not something that's recently out yet, but you can certainly see, and things like the top 500 list, which is the biggest supercomputers in the world, you can really see the rise of China in particular on those lists and the investments that they've been making to have bigger computers.
Because the elements that you need only are U.S. and China: big data, big compute, right? And in a hardware ecosystem. Who else has that, right?
Yeah, I mean, so certainly, like there are individual places where you can see things. So, for example, some of the weather modeling that is done in Europe is very, very good, right? And they're starting to think about adding machine learning into that, right? But it tends to be like, that's an example where these big meteorological groups within those governments have supercomputers, they have lots of hardware, right? And they have a lot of expertise.
But there's a certain amount of vertical integration, right? So all the way to local hardware ecosystem, right?
That's right. Well, and in particular, I mean, another implication for businesses is this idea that you may need to integrate more all the way up. So if you're somebody like Google and you're saying we're not just going to design software, we're going to design our own specialized hardware to do exactly the kind of deep learning we want to do, right? Then that integration becomes even more important. Right, that you can think about, that you have that design expertise in your country, and you can bring it inside. You have that expertise to tie that into the operating system and ultimately the API that you want people to use for it.
And with that, thank you, Neil Thompson. This has been great, and we'll definitely follow your work in the future. And I'll try to bring you back when you have one of these new papers out. Thank you.
That'd be great, Ben. Good talking to you.